Hi students, here I am Amrita ma'am, your physics teacher. So I am here with the next new chapter, which is current electricity. The current electricity chapter we consider two parts. That I have divided that chapter in two parts, and in two parts we are going to cover all the chapter, and then we'll deal with the numericals which are related to this. Basically, this chapter is the practical knowledge itself. We are going to do practicals on the basis of current electricity chapter. So let's move. What are the points and the part one? Okay, let's move to the next slide. So these are the points which we are going to learn in this particular. First point is Kirchhoff's law. In Kirchhoff's law, we are going to deal with two laws. First is current law, and second one is voltage law. Okay, so this will be the first point. Second point is Wheatstone's bridge, then meter bridge. Wheatstone's bridge and meter bridge, and even the potentiometer. These all other practicals which you all are going to deal with. All these practicals in lab itself. So we are going to do the theoretical study of these 3 points: Wheatstone's bridge, meter bridge, and potentiometer. In this particular part, we are going to see only principle of potentiometer and comparison of EMF of primary cell by using potentiometer. And there will be more two uses of potentiometer that we are going to deal in next part. That will be the part 2. Alright, so these are the points which we are going to deal in this particular part. So let's move to the another slide, which is going to deal with Kirchhoff's law of electricity. Okay. So let's move to the next slide, which is Kirchhoff's law. This Kirchhoff's law, as I told you, it divides into two parts. One is current law and second is voltage law. So in this slide, we are going to learn about current law. Alright. Basically, before going towards current, how do you all know current and how does it form within any electrical circuit? Yes. When charges are flowing from one place to another place in some given time, that is called as current. We usually denote current by R. R is nothing but Q upon T, which is charge enclosed by any junction or any circuit divided by time in which the current is. So basically, I is Q upon T. Unit of current is usually ampere, or it may be milliampere, microampere, etc. Alright. So we are going to deal with the current law, which is given by Kirchhoff. So the current law is stated as every sum of electric current and in any electrical network is always zero. Alright. So when you're going through the statement, you can see a new word, which is junction, is there at the statement. So let's see what is the meaning of junction. Junction is nothing but a single point at which current is either coming or going away from that point. It is a single point at which current from any direction comes at that point, or it can go away from that a single point. It is there inside any electrical network. So that is called as junction. Alright. So what is the role of junction in this current law? The role is the algebraic sum of electric current at a junction in any electrical network is always zero. In mathematical form, you can say that summation I is equal to 0. Okay. So let's see the diagram. I have given the diagram in various colors. Red color denotes the current which is going away from this junction. In this diagram, it is a single point at which current is coming towards it, or it is going away from that. Alright. So I2, I3 and I5 are three currents which are going away. We will denote by red in this diagram, and green has been denoted when current is going towards the junction. So I1 and I4 are currents which are going towards. Alright, so this is the diagram which denotes and current in this electrical circuit. So when we are saying algebraic sum is 0, we have to consider some sign convention which apply to the current. Right? sign convention may consider as when the current is flowing towards junction, and it may be considered as positive, and when it is going away from the junction, it may be considered as negative. So let's see what is the sign convention for the current. Right? So there are two sign conventions. First one is the current toward the junction are taken as positive. The incoming currents towards the junction are taken as positive. You diagram green, which is I1 and I4, which are coming towards the junction. Incoming currents are there. So that should be considered as positive. And what is remains? Currents which are going away from the junction, that would considered as negative. So I2, I3 and I5 are the three currents which are moving away from the junction node. So that will be considered as negative. So according to the current law, we can write this in equation form as I1 positive. So I1 minus I2 minus I3 plus I4 minus I5 is equal to 0, because the algebraic sum should be equal to 0. This is the Kirchhoff's current law, right? So you can rearrange this equation and then write this as I1 plus I4, both are having plus sign. I1 plus I4 is equal to I2 plus I3 plus I. By moving I2, I3 and I5 to the another side, that will change the sign from negative to positive, because we are changing the side of all this current. So that will balance the equation. So that will be I1 plus I4 is equal to I2 plus I3 plus I5. So that you can write also, right? So this is nothing but Current's law of Kirchhoff. It states the algebraic sum of all the electric current at a junction in any electrical circuit or any electrical network is always 0. Mathematically, it is summation I is equal to 0. So here is another law of Kirchhoff, which is voltage law. Current law we have already seen, that is summation I is equal to 0. Right, so let's move towards our voltage law, or it is also called as loop. Now you may have query, what is loop? Loop is nothing but any closed path which is there inside electrical circuit. Alright. In this voltage law, we have to consider some tracing path, and in that we are going to consider the sign convention as we have seen in current law. Alright. So let's see what is voltage law. Statement is the algebraic sum of all the potential drops and EMF along any closed path in an electrical network is always 0. Again, I am telling you, algebraic sum of potential drop, that means V. Algebraic sum of V and EMF, that means E. So, V E is equal to 0. According to Ohm's law, but I into R. So the law stated as summation IR plus summation E is equal to 0. Right? So let's move towards the next point, which is sign convention. As we have seen sign conventions for current law, we have to consider sign convention for EMF as well as for potential. That is B, right? So let's see. Before moving towards the sign convention, I have to tell you one thing. When you are going to the sign convention, you have to consider the path which is being traced. You are going to decide the path. It may be clockwise or it may be anti-clockwise. In this case, I am going to consider a path in two parts. Alright, you can see the diagram here. The diagram is having 3 resistances and 2 EMFs, and current is given. Direction of current is also given. So there are two loops. There are two closed paths that we can consider. First closed path is A B C A, upper triangle, and second path is lower triangle, which is A C D A, and wholly you can say A B C D A. All right. So I am going to consider by using two loops first loop that I'm going to consider is ABCA, first triangle. Okay, so tracing the path in this manner from A to B, B to C, C to A. That is the consider. Alright. So let's see what are the sign convention in that case. First sign convention is of EMF. The EMF is taken negative when it transfers from positive to negative terminal of the cell. That means if tracing a path in the given manner A, B, C, A, if I am considering from A to B first, in A to B, the cell is or the EMF is transferring from positive terminal to negative terminal. So it's negative. In this case, it is negative. I am transferring the EMF from positive to negative terminal. That's why it is negative. If I am tracing path from B to A, then it will be from negative to positive of even. So that may be, not maybe, that will be positive. Alright. This is the sign convention for EMF. It is negative when transfer from positive to negative terminal. Okay. The next sign convention is the EMF is positive when we transfer from negative to positive. As we have seen, if I am considering from A to B, even will be negative. And if I am considering the path from B to A, that will be positive even, right? The next is for, that is for B. So we have to consider the direction of current. If I am tracing the path from any direction, in this case we are taking path from A to B, B to C, C to A. Alright. While traveling from A to B, current is in opposite direction of our tracing path. That is I1. So that is taken as positive. If the current is going along with us, along with the tracing path of us, then it is as negative. In this case, from A to B, current is I1 and resistance is R1, which is in opposite direction of our tracing path. So that must be positive. Next, B to C. Only current is there, no resistance. So we can skip this part. From C to A, current is I1 plus I2 and resistance is R2. Again, this is in opposite manner. As we are tracing the path from C to A, current is moving towards point C. Alright, so this is also positive. So, according to voltage law, the summation of EMF and summation of potential drop, it should be equal to 0. So we can write the equation minus E1 plus I1 R1 plus I1 plus I2 into R2 is equal to 0. In a similar manner, you can do it for C, D, A. So let's see what will be that. From A to C, current is going along with the tracing path. So it should be negative. So minus I1 plus I2 into R2. Now from C to D, current again is along with the tracing path. So that must be minus I2 into R3. Now for EMF, we are tracing the path from C to D and EMF will be transferring from negative terminal to the positive terminal. So it should be, it should be positive. So you are getting equation as minus of I1 plus I2 into R2 minus I2 R3 plus E2 is equal to 0. Okay. So in this manner, you are going to consider the signs for voltage, that is potential drop, as well as for EMF. Alright. What is the sign convention for EMF when tracing the path, and while tracing path, if is transferring from positive to negative, that must be negative. And when it is from transferring from negative terminal to positive terminal, that must be positive. And while tracing the path, if current opposes the path, then it is taken as positive. And while tracing path, if current is flowing along with us, it should be negative. So this is all about Kirchhoff both the law. First law is for current and second law is for voltage. Okay, so we have studied both the laws. First law states as mathematical statement is summation I is equal to 0, and second law is for voltage, that is summation IR plus summation E is equal to 0. Okay. Okay, so the next point is Wheatstone's bridge. Now, what is Wheatstone's bridge? Wheatstone's bridge is invented by a scientist whose name is Wheatstone. So it is named after him. So that is why name is Wheatstone's bridge. Now, why the bridge over there? You can see the diagram which is there on the side. In that slide, you can see 4 resistances are there and they are connected in particular manner. That particular manner in this diagram is quadrilateral. So you can see P, Q, R, S are the 4 resistances that are connected in quadrilateral shape, whose name is A, B, C, D. Alright, so we are connected in that manner. And you can see another one quantity which is galvanometer is connected between 2 points which is B and D. So that works like a bridge between A and C. You can see from A to C 2 resistances which is in upper part of the loop, and below there are 2 resistances. So you can see there are 2 paths from A to C. While considering A to C, A, B, C is one path, A, D, C is another path. Between the both paths, there is a bridge. In the bridge, we have connected galvanometer over there. Now, why galvanometer is connected? Because the current which is flowing in that is very less. So that's why we are connecting here a galvanometer, not any ammeter or not any milliammeter. So that's why there is a galvanometer over there. Alright. So all this is connected across a cell and a key, obviously. When key is open, current will not flow through the circuit. When key current will flow through the circuit. So while current is flowing, I is current which is flowing throughout the circuit between all the resistances, and at point A, the current is divided into 2 parts, which is I1 and I2. You can see in the diagram from A it splits between I1 and I2. Moving towards B it is I1, while moving towards D is I2. And the current which is going towards G, which is galvanometer, is IG. Now, as we are saying, the bridge is there. The bridge is balanced or unbalanced. In this case, we are going to say the bridge should be balanced. Now, how the bridge will be balanced? The condition to balance the bridge is current inside galvanometer should show 0. That is, null deflection will be there. Now, how the current will be 0? According to Ohm's law, V is equal to IR, right? So, I is equal to V upon R. So, you can see R is not there. But if V, that is potential difference, if it becomes 0, then I can be 0. So, how V will become 0? As it is connected between 2 terminals of quadrilateral, which is B and D. So, potential difference will be VB minus VD. If this difference becomes 0, the current which is there across galvanometer will be 0. So, how it will be 0? You can balance the whole Wheatstone's bridge by equipotential condition. That means potential at B should be equal to potential at D. If potential at B and potential at D becomes equal, then the difference between will be 0 and the galvanometer will show zero deflection. Then and only then we can say whole bridge is balanced. So balancing for distance bridges, galvanometer should show zero deflection. Why it is showing zero deflection? If potential difference is zero, B and D becomes equipotential, then the current will be zero. Alright, so to prove all these things, we are going to apply Kirchhoff's law. Kirchhoff's loop rule we are going to apply. So for the loop, we are going to consider two different loops. First loop is B, D, A, and second loop is B, C, D, B. While considering A, B, D, A, by applying Kirchhoff's both law of current and law of voltage, we can say we have to consider a sign convention. While tracing path, if current is going along with us, then it will become negative, and if the current is applying in opposite direction while tracing the path, then it will be positive. So let's see what happens to the first arm, which is A to B. While moving from A to B, current I1 is moving along with the tracing path. So it will be minus. So you can say minus I1 into P. Next, from B to D. From B to D, current is Ig, and the resistance which is across G, which is G itself, capital G, you can say the resistance across the kilometer. So that will be along with the tracing path. So again it will be minus. So minus Ig into G. While moving from D to, current is in opposite direction of the tracing path. So it should be positive. So it is plus I2 R, I2 R. So summation of this all should be 0 according to the law. So it is minus I into P minus Ig into G plus I2 into R is equal to 0. So this is the first equation getting. Now we are going to consider the second loop. The loop which is BCEA. By considering the second loop BC, you can apply the same rule. See, now you can ask the question like from B to C the current is I1 minus G. Why is it so? While I1 is split by A, at point A the current is splitting into two parts, right? I1 and I2. While moving from G, B is the point which is connected to G also. So the current should be considered D, which is through galvanometer, and it is away from that D, away from that galvanometer. As you can see the direction of that current, it is moving away from the galvanometer, so it should be minus. So that's why current at B is I1 minus Ig, as it is moving away from the junction, you can say. The current at B is I1 minus G. Similarly, you can say D. It is moving towards galvanometer, so it is plus Ig. That's why I2 plus Ig is there. Consider the second loop, which is BCDB. To see current is moving along the, so that's why you can say minus into bracket, because there are two currents, so we are putting a bracket. Minus I1 minus Ig into resistance is Q, right? So Q. From C to D. From C to D, while moving from C to D, current is in opposite direction of tracing path. So that will be positive. So positive of I2 plus Ig into resistance is S. So into S. Now from D to B. From B to B, it is current is Ig and resistance is G. Why is it positive? Because we are tracing path from D to B and current is in opposite sense. So that is positive. So it is plus Ig into G is equal to 0. So these are the two equations. By applying Kirchhoff's law, both the laws. Alright. Now, as we said, this all bridges said to be balanced if and only if the current which is between galvanometer will show zero reflection, then it is balanced. Now we are going to put value for Ig is equal to 0 in both the equations which we have derived from applying Kirchhoff's law. Alright. So let's see. By putting Ig is equal to 0, what we can get by considering first equation, by putting Ig is equal to 0, second term will get cancelled. We are getting only two terms, which is minus I1 into P plus I2 into is equal to 0. Now let's consider second one. In second one also, Ig, while putting Ig is equal to 0, we are getting two terms. Okay, alright. In both the terms, you are getting I1 minus Ig is there. We have to P is equal to 0. So you are getting only I1 into Q minus I1 into Q plus I2 into S is equal to 0. This is what you are getting because Ig is 0. Alright. So from the first equation you can write I2 into R is equal to I1 into P. As there is a negative sign is there, so we have write in positive sense. So is equal to we have written. So I2 into R is equal to I1 into P. And by considering second equation, you are getting I2 into S is equal to I1 into Q. You can see your calculation. Now, after dividing both the I2R I2S is equal to I1P divided by I1Q. What you can get? I1 will get cancelled and I2 will get cancelled. You're getting a balancing equation as P upon Q is equal to R upon S. So this is nothing but the balancing equation for Wheatstone's bridge. Alright. I hope you got this. Let's consider again. I will explain again. Wheatstone's bridge is the bridge in which four resistances are connected in quadrilateral sense, and between 2 points of the quadrilateral galvanometer is connected, and to balance the Wheatstone's bridge, galvanometer should show zero reflection. Now we are applying Kirchhoff's law. Two loops are there. To apply the Kirchhoff's law to both the loops, we can get two equations. In that equations, we can put Ig is equal to 0. By putting Ig is equal to 0, you are getting two equations which are in terms of P, Q and I1, I2. You can divide both the equations and you are getting finally the equation as P by Q divided by R by S. Now, there are four resistances and the ratio is there, the equation. So, if we know three of them, you can calculate one of them. If three resistances are known to us, you can find out the value for the fourth one. This is what the application of Wheatstone's bridge is. Now we are going to see the applications of Wheatstone's bridge, where it is and how it is used. That we are going to see. You can have a look inside the slide again, and then you will come to the principle of Wheatstone's bridge. Okay, so we will move towards the application of bridge. So here is the application of Wheatstone's bridge, and the application whose name is meter bridge. The news we are going to perform this experiment in lab also, so you will come to know how does it works. So here is the diagram showing the exact arrangement of this meter bridge. What is meter bridge here and why is it called as meter bridge? Because there is an arrangement of a wooden board on which 1 meter wire is connected between the point A and B. You can see the diagram. I am explaining by looking at the diagram. Between A and B, the wire is there, which is uniform, and it is of 1 meter. It should be shouldered between the point A and B, and it should be uniform, so that will get the exact reading. So between A and B, there are three strips. These three plates are conducting. They behave like a conductor. They are usually of plate brass, so that the current will through this. So that is of L shape. And you can see that is of L shape, and in between them there is another plate named C. Right? Between first gap of the strips, that is called as LG, left gap, and another gap is called as right gap, obviously. Now, in left gap or in one of the gaps, one resistance is known to us and another resistance is unknown to us. So by using this, we are going to find out the value for unknown resistance which is there in any one of the gaps. Okay, so here we are connecting the unknown resistance, which may be a wire which is wound on the wooden strip. We are going to find out the resistance which is there inside that wire that is connected between the left gap, and known resistance means resistance box which is having number of resistors, but looking the pin you can get the value for resistance, and that is connected in right gap. You one who is going to decide which amount of resistance you are going to remove from that box. So that is in another gap. Between A and B, battery, key and rheostat is connected. And to the point or between point C, one terminal of the galvanometer is connected to C, and another terminal is connected to the jockey. The jockey is used to find out the equipotential point on the which is there on the wooden board. So as we said, it based on the principle of Wheatstone bridge. So galvanometer should show zero deflection. When the galvanometer will show zero deflection, if it gets two potential points, that means potential at C should be equal to potential at some point. Here we are going to say another potential point is B. You can get anywhere along the wire that you are going to find out, and this is the experiment. You are going to find out the equal point at which galvanometer will show deflection, or you can say null deflection. So for that, we are going to take off number of resistances from resistance box. Suppose I am plugging 100 ohm of resistance from resistance box. I am going to find out by touching the jockey on the wire where we are getting the deflection. After touching the jockey on the wire, you will get some deflection, and the current is flowing throughout the circuit. It will show some deflection. One is there on the wire where galvanometer will show zero deflection, because there should be a equipotential point. So the point where the galvanometer is showing zero deflection, we are going to touch that jockey over there, and we are going to see what is the length at which we are getting the equipotential. Now, how to find out what is the length? For that purpose, scale is attached on the wire. Scale is there. Using that scale, you can find out the length. So the length which is related to X, which is unknown resistance, is known as Lx, and the length which is to the right side of the point D, potential point, it is known as Lg or Lr, whatever it may be. So there will be Lx and Lr, Lx or Lg. It may be respective to the diagram. Here it is Lr, because it is the resistance box over there, so we are going to say it as Lr. So by using principle of Wheatstone, the balancing condition will be 4 resistors and the ratio of that. So X upon R is equal to resistance which is along the wire, which is R AD divided by R dB. Because when you are going to touch the jockey on the wire, the wire will get converted into two different parts. First part is to the left side and another part is to the right side. So left side is related to unknown resistance and right side is related to the resistance box, which is known resistance. Going to find out the value for RAD and RDB. So as the wire is uniform or the wire is same throughout the experiment, so we can consider another new term, which is rho, which is the resistance. What is the value for rho? It is Ra upon L. By you can find out value for Rad. Rad is equal to rho L Ad divided by A. Rd is equal to rho L dB upon A. We are going to take the ratio of both of this. So as we are taking a ratio of this both, rho will get cancelled because the wire is same. So you are getting X upon R is equal to Lx upon Lr. So by knowing value for R, which is there in resistance box, and knowing value of Lx, which we are going to find out by jockey, and Lr by touching the jockey on the wire, we can find out value for Lr again. So you can find out the value which is unknown resistance. This is all about the meter bridge. This is very easy one experiment by using which you can find out the value for unknown resistance. Now, what are the precautions we have to consider while doing all this experiment? First one is the wire should be uniform. If the wire is not uniform, you are not getting the exact string. So wire should be uniform. Wire should be shoulder and point A B. That is the second precaution. And third precaution is to maintain that uniformity of wire. Jockey should not slide on the wire. It should only touch to the wire. If you slide the jockey, it will lose the uniformity of the wire. And what will be another one precaution you are going to take is you are going to take off the resistance from resistance box in such a manner that you are getting all the readings in between, midway of the wooden bridge. Between 30 to 70 you are getting the readings, or 40 to 60. In between 40 to 60 you are getting all the readings. You are checking 3 or 4 readings from resistance box. 3 or 4 resistances you are going to take off, and along with that you are going to find the value of and to minimize the error, we always do 3 or 4 readings, and by taking all the 3 or 4 readings, we take the mean, and then we take the final reading. So in that manner, we are going to take 3 or 4 readings, and also another one activity you can do by using this experiment is you can interchange the position of X and R. After doing 3 readings, you can exchange the position R in left hand and X in the right hand. You can take you can apply same procedure and you can take all 3 readings again, and then you can take the mean and you can have the final value for X. So this is all about meter bridge. You are going to perform this experiment in laboratory, so don't worry to perform, and then you will come to know, or you will overcome all the queries which are there inside your mind. And if still you are having some query, you can ask in comment box. Okay, so here I am uploading one original image of the meter bridge, so you can have a look in another slide which is having original image of meter bridge. So here is the original pic of the meter bridge. We are just going to replace that battery, that means E, battery of EMF E that we have said. We are not going to use this kind of battery in the earth. We are going to use another kind of battery limiter we are going to use. All other terms are same. You can see metal strips are there, scale is there, jockey is there, director is there, and resistance box is there. All are there. Key is there, one-way key is there, and one gap is vacant over there. At that point, we are going to attach one unknown resistance, which is wire wound on a wooden strip that is going to attach in the left gap. Okay, so this is the original pic. Potentiometer. Potentiometer is a device which is used to find out potential difference between the 2 points and are connected by conducting wire. Even potentiometer is used to find out EMF of a cell, to compare EMF of two cells, and to find out the internal resistance of a cell. In this slide, we are going to explain principle of potentiometer and how does it work, that we are going to see in this slide. So you can see the circuit diagram as well as the original peak of potentiometer. Basically, potentiometer is a wooden board on which a scale is attached to it, and there are 2 points which we are going to find out the potential difference, point A and point B. They are connected by an uniform conducting wire which is arranged in zigzag motion. So it is about 4 meter in length, minimum 4 meter in length. As we increase that length, what happens to it, we'll see here in this as a principle. So the circuit diagram is there. Now we'll see what is the principle. Principle is the potential difference across any length of wire of uniform cross section and uniform composition is proportional to its length when constant current flows through it. What are the terms which are included in principle? First is uniformity of cross section and composition of the wire, and constant current. These 2 terms we are going to see in principle, and what we are getting, that V is proportional to L, that is length. So it is very simple to remember that V is proportional to when composition of wire and area, that is cross-sectional area, is uniform and current which flows throughout the circuit is constant. So you can see the circuit diagram of potentiometer. Point A and point B are the 2 points across which we are going to find out the potential difference. To find out that, we have connected voltmeter over here. One terminal is connected to point A and another terminal is connected to the jockey. By using the jockey, we are going to touch the jockey on the wire and we are going to see what deflection it shows in voltmeter. Battery of EMF E. To flow the current, constant current to it, we have connected the ammeter here, rheostat and key. All 4 components are connected across A and B, as you can see in the diagram. And it is written from A to first metal strip it is 100 centimeter. From that again to another strip it is 200. In this sense, point B is at length 400 centimeter or 4 meter. So this is a potentiometer of length 4 meter, having wire 4 meter. So as an example, we can say when I am touching the jockey at distance 100 centimeter, if the voltmeter is showing 5 volt of voltage, then I am going to touch the jockey at point 150, then the voltmeter is showing 7 volt. If I am touching the jockey at point 250, then it will be showing 14 volt. If I am touching the jockey at point 300, then it will show again the next, which is maybe 16, maybe 17 volt. So in this way, as I am increasing the length of potentiometer wire, the voltage across it or potential difference across both points goes on increasing. So this is nothing but the principle of potentiometer. Now to prove that, we have derived one equation which is very simple. As you all know the Ohm's law, which is V is equal to IR. Instead of R, we are going to put one value which is related to resistivity. Resistivity is related to the conducting wire which is there between the point A and B. So resistivity is denoted by rho. You already have learned this, and the formula for resistivity, that is rho, is RA divided by L. We are going to put that formula in this. Then you are getting V is equal to I rho L divided by A. As we have said, current flowing through the circuit is constant. It is uniform wire, so area is constant and so resistivity is constant. So all the terms are constant except length. So you can say V is direct proportional length. As constant current, constant resistivity, and constant area is there. So you can say V is proportional to length. So as we increase the length, V will also increase. So that is nothing but the principle of potentiometer. So you can say V is equal to K into L. To know the proportionality sign, we have multiplied here by a constant term, which is K. Or you can say V upon L is constant. So this is nothing but a potential gradient. This is called a potential gradient. So this is all about the potentiometer. And the graphical representation of this is given in this. V and I plotted against each other, and it will be a straight line, and it is passing through origin O. It is linearly increases, not non-uniform. It is uniformly increases. So it is a straight line, and it is passing through origin. So this is the graphical representation of this. This is all you are going to study in laboratory. Also, we are going to perform experiment by using this potentiometer. We are going to deal with all the uses of potentiometer in laboratory. As we have discussed the use of potentiometer and principle of potentiometer, which is to find out the potential difference across the 2 points. Now a question may arise: voltmeter does the same work, so what is potentiometer? What are the advantages of potentiometer over voltmeter? So this chart is showing the advantages of potentiometer over voltmeter. You can have a look at this slide, and we'll discuss one by one. First point is written in this is potentiometer is more sensitive than voltmeter, and voltmeter is less sensitive than potentiometer. So this is the first one. Second, the main thing, it is written in this slide. So the main thing is, as we increase the length between the 2 points, or as we increase the length of potentiometer, we can increase the voltage. So this facility doesn't available in voltmeter. Voltmeter is a device which only gives you potential difference across the 2 points. It will give the reading for voltage only. But potentiometer can be used to measure potential difference as well as the EMF, and also to find out the internal resistance. So this is the main advantages of potentiometer. So the second point, as we have said, a potentiometer can be used to measure potential difference as well as the EMF of a cell. But voltmeter can only measure the potential difference. It is used to find out the potential difference, voltage. That's it. Third advantage is measurement of potential difference or EMF is very accurate in the case of potentiometer. By using potentiometer, we can calculate accurately. And as voltmeter can only measure potential difference, it is less accurate, as it is given a scale on that. In that scale, we have to measure the readings, and that may be have some error. It may be have instrumental error, or it may be have personal error. List count of potentiometer is much better compared to voltmeter. Obviously, list count is very easy of potentiometer as compared to voltmeter. As we change the voltmeter, the list count will change. It will vary from 1 unit to another unit. Voltmeter of the range 10 volt may be there, 5 volt may be there. So list count will go on changing. So the voltmeter can measure potential difference of the order of 10 to minus 6 volt. That is the list count of voltmeter, but it may vary from 1 voltmeter to another voltmeter. It is having range of that. And potentiometer is having a length which is applied between the 2 points. When we increase that length, only then voltmeter value of voltmeter will also increases. So this is the points which we have discussed that are advantages of potentiometer over voltmeter. Not only the advantages, it may have the demerits of potentiometer over voltmeter. There is a homework to you all, that after doing principle after studying advantages of potentiometer or voltmeter. Just think on that and what will be the demerits of potentiometer. Think on that and comment below the video. Okay. One of the use of potentiometer is comparison of EMF of two cells. We are going to use the principle of potentiometer over here to compare the EMFs of two cells. The circuit diagram shown over here, A and B points are the points of potentiometer, which is connected by long conducting wire of 4 meter approximately. Between the points A and B, battery of EMF E, key K, and rheostat is connected. And the battery whose EMF is to be compared are connected at point A. Both of them is connected to individual keys and that are connected to galvanometer and that is connected to jockey. This is a short. Now we'll see in detail. A point. A point is connected to positive of all the three batteries. First is E, second is E1, third is E2. The three are the batteries whose positive terminal is connected to A. This is first point. Negative of all the batteries are connected to keys. That means negative of E is connected to key K. Negative of battery E1 is connected to K1. Negative of battery E2 is connected to K2. Both terminals of K1 and K2 are connected to galvanometer G. And negative of it is connected to jockey. Here at another side, key is connected to rheostat and rheostat is connected to point B. So this is all about the circuit diagram. What will be working and on which principle it is going to use, that we are going to see. This is null deflection method. And what is null deflection method? We are going to find out the balancing point at the wire. Balancing point means when you are going to touch the jockey on the wire, we'll see zero deflection on galvanometer. That means at that point, at that positive point, whole circuit is balanced, so it is showing zero deflection. In this case, we are going to deal with individual cell method. What is individual cell method? We are going to tackling of individual cell. Both cells at once will not be working. Only one cell at once will be working and then the second cell will be working. We are going to take readings of individual cell. Main condition for this is battery of EMF E, which is the main battery, should be having larger EMF as compared to E1 and E2. Key K, which is the main key, should be closed always, because when the key is open, current will not flow through the circuit. When key is closed, current will flow through the circuit. These are the two conditions to do the experiment. Now, individually we are going to take the reading. That means, first is we are going to deal with EMF of cell E1. To find out the EMF of cell E1 or to find out the balancing length for the first cell, we are going to keep K1, which is related to E1, closed. Key K1 should be closed and key K2, which is related to E2, should be open. As I said, when key is open, current will not flow through that cell. When key is closed, only then current will flow through it. So I am going to take out the key K2. It will be open. Then current will be only flowing through E1, not through E2. As the current is flowing through E1, galvanometer should show some deflection, and we are going to find out the deflection point. So by touching the jockey at different points, we are going to find out the balancing point at which galvanometer will show the reflection. Suppose that length is L1. Then we are getting equation according to principle that will be E1 is equal to K L1. Okay. So now we are going to see the EMF of second cell, which is E1. What we can do now? We can open the key K1 so that current will not flow through E1. Current will only flow through which cell? It will be flow through only E2. For that, K2 should be closed. So now the second condition is we are going to open the key K1 and close the key K2. When key is closed, current will flow through the second battery, which is at the EMF E2. Now as the current is only flowing through E2, it will show some deflection in galvanometer. Again, in the same manner, we are going to touch the jockey at different points and we are going to see where the circuit is balanced and where is the balancing point. Suppose that point we found it as Q is equal to KL2. So as the wire is uniform, so K, which is constant term, and all other terms which are not considered here, but it will get cancelled. And when we take ratio that E1 on E2, we will get it as L1 divided by L2. So we can compare EMF of both the cells as we know the value of L1 and L2. So the ratio of L1 and L2 will give you the ratio of E1 and E2 itself. And if you know one of the EMF, if we know the value for the EMF E1, then you can find out value of E2 by using this formula. So this is the comparison of EMF by using potentiometer. Main conditions are we are going to deal with null deflection method and EMF. Battery EMF E should be large by E, and key K, which is the main key over there, should be closed only, and then visually react to keep the key K1 and K2 closed and open. In this manner, we are going to do the experiment of this. These are the points which were covered in this slide, in this part, which are Kirchhoff's law of electricity. Both law we have discussed. First, current's law, which is summation I is equal to 0, and second, which is Kirchhoff's voltage law, which is summation IR plus summation E is equal to 0. That is seen in this slide. And then we have in Wheaton's bridge how it is balanced. Condition is P by Q is equal to R by S. When P, Q, R, S are arranged in quadrilateral form, when it is balanced, then we can get the balancing, which is P by Q is equal to R by S. Next is meter bridge. Meter bridge is the application of meter bridge, Wheaton's bridge, and experiment which we are going to deal with this in laboratory. So we have discussed meter bridge also, and next point is potentiometer. In potentiometer, we have seen principle of potentiometer, which is V is proportional to L when current flowing through the circuit is constant and resistivity is constant. Even the resistance R is constant, then only V is proportional to L. Second is advantages of potentiometer over voltmeter that we have discussed in this, and comparison of EMF of cells that we have discussed. Individual cell method, study the individual cell method we have discussed in this part. So all of these points are covered in this slide. I hope you understood all the points. If you have any query, please do comment. Please go through this part and comment in any case of query. And I have given you some work in the Twitter 2, that is demerits of Twitter, that you're going to think on it, and you all are going to comment for that demerits of potentiometer. So let's see how many of you have seen this. Last but not the least, thank you so much for watching the PPT, and I will be uploading part 2 very soon. Thank you so much.